All right, it's a pleasure to introduce Professor Anand Srivastav from the University of Kiel in Germany. Professor Srivastav obtained his early education right here in Deyalbach and Germany, and earned his doctorate in mathematics on functional analysis from the University of Münster in 1988. He was a postdoc and assistant professor at the Research Institute for Discrete Mathematics in the University of Bonn from 1993 to 1998. He has been a visiting professor at several places, including the University of Minnesota, New York University, Yale University, and Humboldt University in Berlin. Since 1997, he has been the director of the Department of Computer Science at Christian Albrechts University of Kiel, Germany. He is also the director of the Computational Science Center at the University of Kiel and a member of the executive board of the German Indian Society. His research interests include discrete mathematics, randomized algorithms, combinatorial and large-scale optimization, discrete Fourier analysis, discrepancy theory, and additive number theory. And his title is right there, Efficient Algorithm, I can't say it, for hard combinatorial problems in hypergraphs.
Thank you very much for the kind introduction, and I would like to thank the organizers, especially Vishal, for inviting me to this very nice workshop. Today I will speak on combinatorial problems, and there's no quantum in the title, but at several parts of the talk I will touch the quantum computing idea. So here's an outline. We will briefly talk about combinatorial complexity, then about some problems in combinatorics where we have done some work and where the connection to quantum computing is there, in particular hypergraph coloring. And in the last part of the talk, I will mention some new paradigm in the design of algorithms, which is somehow the theme of algorithm engineering, and explain the ideas on the problem of matching in hypergraphs. So since the auditorium is quite diverse from experimental physics to theoretical mathematics, I will keep the presentation at a more introductory level, but feel free to ask any questions during the talk. So this is one slide about combinatorial complexity, and maybe the core of computer science today. So computer science is dealing mostly with finite problems, and this means that the problem can be decoded in a computer using finitely number of bits. Now, among these finite problems, there are those problems which have a very specific property. This is the so-called class NP here. And these finite problems have the property that if you give me a solution for these problems, then I can verify the solution in polynomial time. This is not the case, for example, for solving finite problems like Diophantine equations, where you have equations like x squared plus y squared plus z squared equal c, and you are looking for a solution in the integers. Such problems are beyond the class NP. They are, due to the 10th Hilbert problem, undecidable. But here we are talking about decidable problems. So these are all the problems which can be verified in polynomial time. Let's take an example. We take a linear equation, Ax equal b. A is a matrix, x the unknown vector, and b the right-hand side. And if you give me a solution x, then obviously I can test in polynomial time whether this is a solution or not. Another problem would be in graphs. For example, take a graph, and I linear equation, Ax equal b. A is a matrix, x the unknown vector, and b the right-hand side. And if you give me a solution x, then obviously I can test in polynomial time whether this is a solution or not. Another problem would be in graphs. For example, take a graph, and we are looking for minimum spanning trees, and you give me a tree, then I can check whether it is a tree, and I can compute the weight in polynomial time.
Maybe I should interrupt and ask you, what is polynomial time?
Polynomial time means if we decode the problem, say with n bits, then polynomial time means that the computation time is bounded by a polynomial in n. So for example, n cubed, n to the power of 4, or something like this. So any polynomial of the form n to p, where p is a constant, would be polynomial time.
So it's guaranteed not to be exponential, for example.
Exactly. This is the main difference to exponential. So any polynomial is growing much faster asymptotically than exponential. Of course, you can say if we have a high polynomial degree, say n to the 1 million, then it doesn't make much difference in practice to distinguish between exponential and polynomial. But from the theoretical point of view, there's a difference. So this leads also your question to the next class, which is important in NP. This is the class P. These are all the problems in NP which can be solved in polynomial time. And then there's a very strange class in NP. This is the class called NPC, NP complete problems. This is a kind of equivalence class, which means that all problems which are here can be reduced in polynomial number of steps to each other. So they build an equivalence class. And informally speaking, this class has the following property. If one problem from this class is in P, then all problems in NP are in P. So if one problem here is solvable in polynomial time, then all problems in NP are solvable in polynomial time. Take, for example, so of course now we have defined this class NPC, but at the moment we don't know whether this definition makes any sense, whether this class is empty or not. And there's a big theorem of Richard Karp and Cook from 1972 who proved that the satisfiability problem is in NPC. So there is one problem in NPC. This class is not empty. And today we know that there are more than 4,000 problems known which are in this class, and for none of them it is known whether there is a polynomial time algorithms. And this observation led to the conjecture that P is not equal NP, which means NPC problems are there's no NPC problem which can be solved in polynomial time. So examples for such problems are, for example, the famous traveling salesman problem. You have n cities, and you wish to visit every city, but only once, and return where you start. And the tour, this is the so-called traveling salesman tour, should be of minimum length. This is a problem which is here in this class, and one of the most hard problems in combinatorial optimization. So, and the conjecture P not equal NP, or the other way around, there's no problem from NPC, which is in P, is maybe one of the biggest problem of computer science and algorithmic mathematics. It belongs to this problems for which the Rockefeller Foundation has awarded the $1 million if one would solve such a problem. So the conjecture is NP is not equal P. This means that if the conjecture is true, there's no chance to solve NP complete problems in polynomial time. One can solve them in exponential time, but not in polynomial time. Then, of course, the question is whether, I mean, all this theory relies on classical computing, on so-called deterministic Turing machines, the von Neumann concept. And if the conjecture is true, then no thinkable computer lying on von Neumann's concept and Turing machines would be able to solve this problem. And of course, the question is whether with other computing technologies we would be able to attack this conjecture. And it is believed that those who are working on quantum computing say that even with quantum computing power, NPC problems probably cannot be solved in polynomial time. Thus, the hierarchy, the complexity hierarchy, would not break even if quantum computing or quantum computer would exist. Well, this is somehow bad news. But on the other hand, we have to solve hard problems day by day. In industrial applications, these problems come up, and of course we cannot give up because we have an unproven conjecture like P not equal NP. So therefore we have to do something, and because there can be done something not only on the practical side but also on the theoretical side. And thus we are looking here for more examples where quantum computing can reduce the complexity. So if we are optimistic from exponential to polynomial, but even exponential to sub-exponential is a big step. And the other thing which might be interesting is to involve ideas from quantum computing in classical computing. And the question is whether the use of ideas from quantum computing can help to design better algorithms on the computers we have at the moment. So on these two topics I would like to address, and to show you that this is not only wishful thinking, but there's some background and some promising work on the examples of some combinatorial problems. So here's somehow this search problem, which is behind what I'm talking later. So this is somehow the summation. We have a large space which is exponentially big, and we have a very small space which is only polynomially large, and we wish to find a point from the small space. And obviously sampling cannot help here. If you sample with polynomially many with sets of polynomial size, then it already takes exponential time to create the event that such a set would intersect the set S. Now, quantum computing has been applied to some areas, but my feeling is that the whole area of combinatorics, which is more than 150 years old and has shown new algorithmic challenges in the last 20 years, is quietly unexplored and untouched by this area. On the other hand, this area has, so combinatorics offers a universe of problems which might be interesting and promising from the point of view of computing. So among them are coloring theory, the coloring of graphs and hypergraphs, associated discrepancy theory, Ramsey theory, then additive number theory, combinatorial geometry, and combinatorial optimization. And today I will pick an example from coloring theory, discrepancy theory, and one example from combinatorial optimization where we have worked on and where we can see some impact of quantum computing. So geometric and combinatorial discrepancy, so this is one of my favorite subjects on which I worked in the last years. And let me explain you the problem of geometric discrepancy. This is, so forget about the formulas at the moment. So we have here, say, the unit cube in dimension 2, and we have n points. And we wish to distribute the n points in the unit cube as uniformly as possible. So then, of course, the question is, what is a measure for uniformity of distribution? We have only finitely many points. One measure could be to take regular geometric objects and count the number of points which are falling in these objects. And most regular object is a rectangle with upper corner x here. So we take such a test object, such a rectangle, and we count the number of points which are falling in this rectangle, and we compare it to what we would expect if we would have a uniform distribution subject to these rectangles, namely how many points do we expect in such a rectangle. This should be proportional to the volume of the rectangle times the point, times the number of points. So if the distribution would be uniform, then we would expect n times the volume of the rectangle points falling in. And the difference between what is happening and what is ideally expected is the discrepancy of the point set with regard to such a specific rectangle. So this is a geometric measure of uniformity of distribution. Now, of course, we are talking about all rectangles. Then we take the bad guy, so we take the supremum of all the rectangles, discrepancy function, the local discrepancy function, the supremum over all rectangles. And this gives us this, the L infinity discrepancy of the point set with respect to these rectangles. And the L2 discrepancy would be the 2 norm here. So maybe to motivation of this problem, of course, this is mathematically interesting because it is dealing with finite things, and we are talking about uniformity of measures. On the other hand, it has a huge number of applications, for example, in numerical integration. So in numerics is concerned with dimension 2 and 3. There you can do a lot of numerics and finite element methods and so on. But once you go beyond dimension 3, so suppose we are in dimension 10, and you have an integral in dimension 10, then it is already almost impossible to compute such a function. So the numerical methods using meshes show a complexity which is exponential in a dimension. So therefore, if you have n cube complexity in dimension 3, then you would have n to the d in dimension d, and this is not acceptable and not doable. And there the idea is to use kind of point sets to compute such hard functions taking discrete values of the functions on these point sets. So this is the idea of Monte Carlo. If you generate them randomly, you do the Monte Carlo generation 1 million times and then do the computation. And the idea is, if we are not doing randomly, can we find better point sets? And there's some deep theory behind randomness and somehow quasi-randomness. And so the sense of the story is that randomness is not so good as one would think. The quasi-randomness is theoretically and practically much, much better. So we have defined the discrepancy of one point set, and the discrepancy measure or the invariant of this problem is the following thing. We are looking for the point set which minimizes the discrepancy. So we are looking somehow for the best point sets which gives the smallest discrepancy. This is the L infinity norm, or D infinite NC. And the same is the definition for the L2 norm. So the question behind this problem is, can we distribute endpoints uniformly, and how uniform can we distribute them? And this question was answered by Klaus Roth in 1954, and later by Baker with some better bounds, and then also with some constructions by Holton. So Klaus Roth is one of the pioneers in additive number theory. He is now 80, and he worked also on combinatorial problems. And for his work in this area, especially Fourier analysis in additive number theory, he was awarded the Fields Medal in 1964, which is the highest prize in mathematics comparable to the Nobel Prize. And he proved that the discrepancy of n points has a lower bound, namely this lower bound. So this is the lower bound, log to the power of d minus 1/2 of n, which means that we cannot distribute finitely many points uniformly in a unit cube. Whatever we do, whatever point set we take, there will be necessarily a rectangle which will cause this error. This is the discrepancy which is inevitable. And now the question is how to construct point sets which are close to the lower bound, and the answer is for the L infinity discrepancy that we can get very close. There exist point sets of this discrepancy, and there's of course a gap between lower and upper bound, and this has been somehow closed by another Fields medalist, by Baker, in 2001. For the L2 discrepancy, the upper and lower bounds are tight. So here we have log n to the power of d minus 1/2 and log n to the power of d minus 1/2. So now back to Monte Carlo. I know that Monte Carlo methods are widely used in theoretical physics. And whenever some computation is to be done, then Monte Carlo methods are the method of choice. So Monte Carlo methods generate n points. And you may ask, how good is the distribution of these n points? So we know that the best possible point sets gives a distribution, a discrepancy of log to the power of d minus 1 or log to the power of d minus 1/2 n. And we can prove that the Monte Carlo point sets have a discrepancy of square root n. So in dimension 2, the Monte Carlo point sets are a magnitude worse than the best point sets with low discrepancy. On the other hand, the Monte Carlo point sets have the advantage they are somehow dimension independent. So therefore, also in high dimension, they might be more useful than these kind of guys, because here we have the dependence of the dimension in the exponent. But from the theoretical point of view, no Monte Carlo point sets can reach the discrepancy of the optimal point sets. So, but this is still a debate which is going on. So for moderate dimensions like between 10 and 50, what is the best method? And this is still not decided. Now here's an open problem which I wanted to communicate to you today. Given a point set P with n points and the number k, can we test in polynomial time what discrepancy it has? Can we decide whether the discrepancy of this point sets to the rectangle we defined is at most k? And this problem is not even known to be in NP. This is due to the fact that we have infinitely many points in the unit cube, and every point defines a rectangle. So this is not known to be NP. Now let me move to another notion of discrepancy. So what we were talking was somehow geometric, some geometry, and here's some graph theory. Both notions of discrepancy are linked to each other, but let me do it separately. So here in the area of combinatorial discrepancy, which is most important for computer science and algorithm design, we have the following object. We have a hypergraph which with a finite set V, so we call the elements of the set vertices, and we have so-called hyper edges. These are just subsets of the set V. So we take a finite set and we take subsets of the set. And the subsets we call hyper edges, and these two objects, the finite set on the one hand side and the collection of subsets, is called a hypergraph. If the edges all have cardinality 2, then this is nothing else than a graph. So we have points, and we connect the points, and this forms an edge, and this is a graph or somehow 2 hypergraph. Now we color the vertices of the hypergraph with, say, colors. Say, take C equal 2. We take 2 colors, red and blue, and we compute the uniformity of this coloring or the balancing of this coloring in the following way. We take an edge and count the number of red vertices in this edge and compare to what we would expect. So if C is equal to 2, then we would expect in every subset half of them should be red, half of them should be blue. This would be a completely balanced coloring. Okay. So, and for a given coloring, the difference between what we expect and what is actually going on is the discrepancy of this hyper edge, and the minimum discrepancy is the discrepancy caused by a coloring which minimizes this function. So again, the problem is, so for C equal 2, we have a hypergraph, so we have a ground set of finite points. We color all the points red or blue, and then we have the subsets, and the subsets should have this intersection property that they should be colored half-half. So if we have a subset of 8 points, then 4 of them should be blue, 4 of them should be red. This would be a kind of transversal to the set system. And now, of course, the question, as in the geometric setting, is whether one can do that. And actually, Joel Spencer proved in a paper which appeared in a transaction of the American Math Society that the discrepancy of any hypergraph is at most square root n, which means there exists a coloring, 2 coloring, which is causing a discrepancy of at most square root n. And this bound is tight. There's a lower bound. There are matrices which draw a hypergraph with discrepancy some constant times square root n. So this is tight, which says on the one hand side that we cannot color the hypergraph in a way that all the edges are completely balanced. We have to make an error which is in the order of square root n. And on the other hand, there exist colorings which achieve this optimal discrepancy. Unfortunately, the proof of this theorem is existential. So this is again the thing. We have a huge space of all colorings. These are 2 to the n. And the proof of Spencer uses the pigeon principle in exponential space, which says there exists something in this space, and therefore it is not known whether a coloring of this order can be computed in polynomial time. And this is, of course, a problem in NP, but the search problem, whether it is in P or not, is not clear. And I have some belief that for special hypergraphs, this problem can be accessed by quantum computing, and we will come to that point a little later. And the special hypergraphs are the hypergraphs in which Klaus Roth was interested, namely hypergraphs of arithmetic progressions. So here we are in the first n natural numbers. So this is our ground set, 1 to n. And what are the hyper edges? The hyper edges are just arithmetic progressions in the natural numbers. So the simplest arithmetic progression is 1, 2, 3, 4, and so on. Another one would be 1, 3, 5, and so on. So an arithmetic progression has a starting point A and a fixed difference delta and some length. So this is the arithmetic progression in the first n numbers, and the hyper edge contains all the numbers which are appearing in this arithmetic progression. So this is not all subsets of the first n numbers, but only a subset which has a very specific arithmetic structure. And you can do the same in ZP, in the group ZP. So again, starting point P, some difference, and some length. On the hypergraph on the first n integers, we call APN, and the hypergraph in ZP, we call APZP. So this is a special hypergraph for which this bound is obviously true, but it is not clear whether this bound is the truth. So, and in fact, one can show the following. So there's a somehow more generalization of the arithmetic progressions. You can do this also in d dimension. Here we have a picture in dimension 2. So we have some arithmetic progressions on one line, this one, and then we have another arithmetic progression. And if we take the Cartesian product of these two arithmetic progressions, then we get this kind of discrete box, this green box. You can do the same here. Then this is one arithmetic progression, and this is another one, and the Cartesian products is this grid with the red points, and so on. So in this way, we can generalize the arithmetic progression to arbitrary dimensions, and they have some meaning. They are motivated by some deep theorems in combinatorics, by Gauss-Witt theorem, for example. So the question is, what is the discrepancy of such special hypergraphs? And I proved with two colleagues, De and Wehr, that the discrepancy of these hypergraphs of arithmetic progressions in dimension d is exactly n to the power of d divided by 4. And this theta d says that there's some constant which is depending on d there. Actually, this is a generalization of the theorem of Klaus Roth, who proved the result in dimension 1. He gave a lower bound. So in dimension 1, let's look here what is going on. In dimension 1, d equal 1, we have here 4th root of n. And compared to the theorem of Spencer here, we are magnitude smaller. So the special hypergraphs have a much smaller discrepancy than the general ones. And the lower bound of 4th root n was proved by Roth in 1964, and it took almost 20 years till Jerry Matuszek and Joel Spencer closed the lower bound by showing that there exists a coloring which achieves the lower bound. And we proved the thing for dimension 2. So let me rephrase from algorithmic point of view. So we know there's a 2 coloring of one-dimensional arithmetic progressions with discrepancy of theta 4th root n. It is open whether one can find such a coloring in polynomial time, because the proof uses again the Pigeon principle in the exponential space. On the other hand, it is known that such colorings with discrepancy 3rd root of n can be constructed in polynomial time. This is a kind of number theoretic algorithm, and with a simple probabilistic method, one can construct a discrepancy of coloring with discrepancy root n times log n. So, but still there is a gap between here and here, and yeah, till now it is not known whether any efficient algorithm can come close to the optimal 4th root n bound. Well, this is a problem which is somehow long-standing or open, and no progress had been made till now. Now in ZP, the situation is even better. So now forget about the C's. This is C coloring. Take C equal 2. Then what do we have for the discrepancy of the arithmetic progressions in ZP? The lower bound is essentially root p, and the upper bound is root p times some log factor. So the discrepancy of the arithmetic progressions when we move from the line to the group is essentially much larger. It is root p, while it was fourth root n in the natural numbers. So the bounds are almost tied up to a logarithmic factor. And again, here the question is whether one can compute such colorings in polynomial time. The proof idea for the lower bound is Fourier analysis in ZP, and for the upper bound, probabilistic method extended to multicolors. And the quantum computing link comes here. So we were talking about the hypergraph over ZP, and we call such a hypergraph shift invariant if there's an edge in the set of hyperedges which can be shifted, and the shifted edge is still in the hypergraph. So the shift is done by multiplying the edge with some number a and shifting it by b. If we take this edge, so the numbers 0, 1 to p minus 1/2, with this edge, one can show easily that the hypergraph of arithmetic progressions in ZP is shift invariant. Now we construct or design a hypergraph which is a sub-hypergraph of this object, namely the following thing. We take EK be as an edge of k shift invariant hyperedges from E, and we assume that the number of these hyperedges is logarithmically bounded in P. We define the hypergraph AP fin be the sub-hypergraph of the arithmetic progressions in ZP, consisting of all edges of the form B plus A times E, so all the shifts of the edges which are in this set epsilon k. So this is a non-trivial hypergraph, and at the moment I don't know whether this hypergraph generates everything here, but it is quite large. So, but this is an open problem. I hope we can say something about that in future, whether this hypergraph is already enough to generate all the arithmetic progressions. So when we are talking about ZP and Fourier transforms, then let's define what the Fourier transform in ZP is. We have a function from ZP to the complex numbers, and the Fourier transform of this function is defined in natural way. This is the sum over all points in ZP times the evaluation of the functions times the exponential function. And in ZP, the Fourier analysis says that we have convolution, we have kind of multiplication property of the Fourier transform, and we have the Plancherel theorem, which means that the two norm of the Fourier transform is equal to the norm of the Fourier transform. But we have, since we are in a finite situation, we have the factor p in addition, while in the continuous situation, this inequality holds without any additional factor. Now for the L2 discrepancy of colorings of this sub-hypergraph of the arithmetic progressions, one can show easily that the L2 discrepancy can be computed in cubic time. This is not much to do. And we proved now recently that with quantum Fourier transform, we need only p squared times log to the power of L plus 2 times p times. So there's an exponential speed up in one of the p factors here. And I guess that the p square lower bound is optimal. We have not proved it, but when there are some papers on L2 discrepancy computation by Vaziranis and others, which say that the p square is the square polynomial is a lower bound, and this is not proven at the moment here for this special case, but I think this can be proved, so that with quantum computing we are coming close to the conjectured lower bound. And the idea here for the proof is that one can decompose the discrepancy function of this special hypergraph in a very specific way, and using Fourier transformation and parallelization, one can compute via the quantum Fourier transform this function, at least one term of this function, very, very fast. So here, as the proof, I think I don't want to go to the details. That's just, I think. So this was one example where we think that, or we see that quantum computing can reduce the complexity for hard combinatorial problems. And the second theme is whether quantum computing can be helpful in classical computing. So, and this is joint work with Professor Padvadam from DI here in Elbach, and one PhD student, Volkmar Sauerland, in Kiel, and we had some earlier work with Dr. Hans Raj, also from DI. So evolutionary algorithms are kind of meta heuristics for searching solutions in exponential space, and they have been successful in some environments, and are not so good in other environments where the knowledge of the structure of the problem is needed to have algorithmic progress. And we thought that we may include ideas from quantum computing here, and these are somehow the paradigms. So quantum evolutionary computing is inspired by quantum computing. The purpose is optimizing binary problems, so integer problems. It works on a population of individuals having complex valued genes in analogy to quantum bits on a unit circle. We generate new individuals by rounding quantum bits with probabilities corresponding to their real parts. So this is in analogy to making observations. We mutate quantum bits to hold higher probabilities of observations similar to the best so far observation by rotating them towards such solutions. This will be defined more detail later. Altogether, we found that the incorporation of these ideas is something which on a lower level of complexity is already there, namely the so-called idea of randomized rounding. Randomized rounding I will explain later. This is a technique which came up in the area of randomized algorithms in the 80s, and which has somehow advanced the design and analysis of randomized rounding. So the randomized rounding idea is the following. Suppose we have some real number qk. Suppose this is 0.7. And we wish to round a bit either to 0 or to 1. Then in the naive rounding process, we would round it up to 1, because the threshold is 0.7. Okay? And we would round it down, we would not round it down to 0. So if the qk would be, say, 0.3, then the naive rounding would say, okay, go to 0. Randomized rounding, in contrast to naive rounding, does the following. We toss a coin, which is a biased coin, and with probability qk, we round to 0, and with probability 1 minus qk, we round to 1. Okay? So if the probability, say, is 0.3, then we round to 0. Sorry, we round to, if 0.3, then we round to 1 with, 0.3, then qk should go to 0 with probability 0.7 and should go to 1 with 0.3. So in this way, we do the right decision in view of the naive rounding, but we leave some flexibility. Okay? And the connection to the quantum computing here is that we have a superposition of states which results in one state by observation. This means instead of carrying on all the vectors, which the 0, 1 vectors, we deal only with some probability vectors. And once we do the rounding, then we fix or observe the 0, 1s which have to be assigned to the kth coordinate of this vector. So this is a kind of simple idea. So instead of doing something which is deterministically but hard constrained, we do a randomized process which is more flexible. We are tossing coins. And the fitness of many observations of individual gene Q determines the best function of the obtained solution. So here's again the idea of quantum bits and probability. The genes are some complex numbers, and the real parts, these are the probabilities with which we round, or in other words, we observe the 0, 1 vectors which we are searching for. Mutation can be formulated nicely with a rotation matrix. Again, we have a gene here, and we wish to generate a new one. And one way to doing this is just move from that complex number to another one, which is on a unit circle. Mutation means we move to another one, but with a small angle, which means that the gene is not too far away from what we have computed so far. And recombination would mean that we choose larger angles. So these are in the ingredients of the algorithm, and here's the result. This is again for the problem of finding the best colorings for the arithmetic progressions. Let me explain you the picture here. So on the x-axis we have the numbers 0 to 30,000. These are numbers of the hypergraphs. So these are the nodes. So this is the n. So we considering hypergraphs where the node number is between 0 and 30,000. And the number of hyper edges for arithmetic progressions is cubic, almost cubic. So for 1,000, we have 1,000 to the power of 3 hyper edges. So already to deal with these numbers is a non-trivial task. So you have 30,000 nodes and 30,000 to the power of 3 hyper edges. It's already a storage problem. So this has been done with some parallel computing techniques. And here's the discrepancy of the colorings which were computed. So we computed 2 coloring, and then we find the discrepancy of this hyper edge. The blue line, this is the simple randomized algorithms. Here the discrepancy or the coloring is computed in a very simple-minded way. For each node, we take a fair coin, and we toss the coin. If a head is coming, then we color the vertex blue. When a number is coming, then we color it red. So this is a fair coin. And the second, the green one, this is the algorithm of Sarkozy. This is a number theoretic algorithm. And I mean, these 2 algorithms were involved before we started working on that. And you see that the purely randomized algorithms show a discrepancy behavior which is something like square root n. Now, this is n to the, actually, if we fit all the measurements here, this is n to the power of 0.44 times 2 times c. So this is close to what we would expect. So theoretically, it is 4th root I mean, the truth or the optimal discrepancy coloring have 4th root n. So the randomized thing is much, much larger. The Gauss's algorithm, this is the green one, shows a characteristic, if we fit it with some function with optimal fit, which is about 0.3 and something more than 0.3. And what was surprising to me is that the quantum evolutionary algorithm beats all these two. And here we have a characteristic of 3rd root of n with some constant. And I mean, we have generated a huge number of hypergraphs here. I mean, the characteristic, of course, you can say, okay, there can be some constants which makes this characteristic not so significantly. But my feeling is that this picture already is a very good indication that the quantum evolutionary algorithm beats everything which every algorithm which has been there for the arithmetic progressions. So what we can prove is that this quantum evolutionary algorithm can't be worse than that one. So there's a theoretical bound, but we cannot prove that it is better than the Sarkozy algorithm. So this is an open problem. On the other hand side, the computational results clearly shows that quantum computing, or this algorithm which borrowed ideas from quantum computing, is clearly better than what we had before. Now, of course, it would be nice if we, I mean, this is the task which we'd like to do, to prove that this is the characteristic, and then we know somehow that quantum computing already in classical computing is worth to be considered. So let me now come to the third part of the talk. I will touch it only briefly. And there's also a link to quantum computing, but somehow it is more discussed in the area of classical computing. And the key word here is algorithm engineering. So algorithm engineering, this is at the moment a priority research program of the German Research Foundation, where 15 universities from Germany are collaborating. And the idea in algorithm engineering is to bring together different communities in computer science, those who are working theoretically and those who are working practically, in order to overcome theoretical deadlocks. And the methodology is described in this picture here. So, this left part of the cycle, this is what theory is doing. So usually we have a problem, then we design an algorithm, we analyze the algorithm, and if we are happy and successful, we can prove some performance guarantees, like for traveling salesman or for matching or whatsoever. And then people are happy and move to the next problem. So this is the way, if you look at the proceedings of Stock or Fox or whatsoever, so you see the same people who have done one problem, and the next year they will do another problem. Once you have the stock paper, the problem is finished. On the other hand, we see that for many problems, this kind of approach leaves the theory in a state of the art which is not satisfactory. For example, for max cut, this is another graph theoretical problem. It has been proven that we can approximate the optimum up to 87%. It is also known that with polynomial time approximation, one cannot do better than 95%. In between, there's a gap. So the gap is not so huge, but since the proof was done, no progress was made. And here, the idea of algorithm engineering comes that once you have such a deadlock situation, why don't you implement the algorithm, see what the performance in experiments is, draw a conjecture, from the experiments, redesign the algorithm, and try to analyze it again. And if we are talking about applications, then of course the inputs should come from realistic models, while in theoretical computer science the models are sometimes a little artificial in order to prove something which can be published. So, but from the realistic models driven, the analysis would be much more difficult. And the crux of this approach is to draw so-called falsifiable hypotheses from the experiments. So from the experiments we have a hypothesis. Either we can verify the hypothesis, then we will have a proof, or we falsify the hypothesis with some counterexamples and so on. But in that way, we keep the cycle alive. So this deadlock situation ideally should not appear, and it brings together the experimental and the theoretical community. And I will show you one example where we are participating in this program, and with one example where this approach has already break the deadlock, and this is concerned with matching in hypergraphs. So again, we have a hypergraph H, and we have a subset of the edges, which is called a matching or a B matching, if the following happens. It is a one matching if these the edges from the subsets do not intersect, if they are disjoint. And it is called a B matching if they do intersect only in a point B times. So, and the maximization problem is to find a maximum number of hyperedges so that the edges form a B matching. In graphs, this is one of the pioneering problems or first problems where polynomial time algorithms was given by Jack Edmonds in the 60s. For hypergraphs, the problem is NP hard only already for 3 uniform hypergraphs. What
exactly is matching?
Yeah. So think of a graph. Yeah? Then a matching is a collection of edges which are pairwise disjoint, pairwise not incident. Okay? And in hypergraph, the same is true. This is a collection of subsets which are disjoint. Yeah? So we have a collection of subsets, and the matching is, has the property that all the subsets which are in the matching do not intersect. So, and the computational complexity here is given here. So for graphs, this is solvable. For hypergraphs, it is computationally hard. So there are many parameters. I don't want to go into the details. And maybe I just go to the picture. So there were some theoretical analysis done. So this is for B equal 1, so matching problem. And so let me explain again the drawing here. So here we have depicted the cardinality of the hyperedges. So this is the size of the subsets. And 3, 4, 5, 6. And say, for example, 4. And here we have drawn or generated a huge number of hypergraphs. So about 10 million hypergraphs who are so-called 4 uniform. The size of the edges is 4. And for each of these hypergraphs, we have applied the algorithms we have designed and the algorithms which were in place. And say we take all the hypergraphs with edge size 4, 10 million, compute the B matching there, and take the worst one. Not the average, sondern the B matching which is worst among this. And this number is depicted here. Yeah? So this is the approximation ratio. This shows somehow how close the number, matching number which is computed is close to the optimum. So this is the percent of closeness to the optimum. So when we see, so these are the, this is the theoretical lower bound, which is something like 1 over L. L is the size of the hyperedges. Then there was an algorithm which is called Oblivious Algorithm. Here we have a performance guarantee of something smaller than 0.4. And then these are the algorithms which came up with the approach of algorithm engineering. We designed the algorithm, we tested it and redesigned it and so on. For these algorithms, we can partially prove that the approximation guarantee is at least 0.4, so it is not worse than that one. But in practice, we see that the approximation is much better. This is something like 0.6. And so here was the theoretical deadlock. So for many years, there was no new algorithm there. And therefore, if you're dealing only with, with a lemon which is already squeezed, then you cannot expect some more juice. And the thing was that no new algorithmic ideas were there, but the people were attacking the analysis with more sophisticated probabilistic tools, and there was only incremental progress. And so he has clearly seen that this, the incorporation of practical work and experimental analysis can help to design better algorithms. And we are somehow optimistic that finally we will also prove that the performance ratio is something like 60%. This is the ultimative goal of this thing. So this is not to do experiments, and so the scientific goal of algorithm engineering is to come up with theories. So we are doing all this to build new theories. And now, to summarize, we have seen that there are problems in which have somehow number theoretic flavor, where quantum computing can reduce the complexity. We have seen also that the qubit compression used in randomized algorithms is helpful, for example, in quantum evolutionary algorithms. And this has been shown clearly by this, I think in combinatorics it's an important problem to compute the arithmetic, discrepancy, low discrepancy colorings. Here a proof would be beautiful, but this is in work. And for future work, the question is, can we find other problems in number theory or related to number theory where we can successfully apply quantum computing? I think this should be possible. So what we have done is somehow the first step. And then back to combinatorial optimization and algorithm engineering. If we don't think of solving hard problems in polynomial time with quantum computing and think of being a little modest, namely to try to accelerate the running time, improve the complexity of already existing polynomial time algorithms with quantum computing, then this could make much more sense than looking at, so there's an exponentially hard problem and we want to do it in polynomial time. And I think here for general combinatorial optimization problems, this is somehow hopeless. But whenever one can make a link where these techniques of quantum Fourier transforms and others are there, there might be a chance. So that's all what I wanted to say to you today.